Using a single-shot response for inter-symbol interference ISI analysis is a handy time domain tool in high-speed communication systems like SerDes because it provides a direct and intuitive way to understand how a channel introduces distortion to the transmitted signals. Then, the single shot helps us easily build up our mental model of recovering the signal from the distortion. We've talked about the concept of single shot or single pulse response several times implicitly. Now, we'd like to emphasize why you need a single shot or single pulse response for your ISI analysis. First, the single shot shows the fundamental representation of a channel loss behavior. If we apply another handy time domain tool, an eye diagram, you will see both eyes closed under any 20 dB and 30 dB channel loss. Then you cannot tell the difference between the 20 dB and 30 dB channel behaviors. Could you tell me why? Correct. Remember, the eye diagram is created by overlapping multiple bits on top of each other. Then, this bit stream passing an ISI channel will cause successively symbols to blur together and cross the eye. Because of the spreading the pulse beyond its allocated UI interval to interfere with neighboring pulses, which was again called inter-symbol interference, ISI. So, what should we do? Bingo! Just make a single shot response instead of multiple shots, which cross the eye. Then, you will easily see the difference of the channel behaviors between 20 dB and 30 dB loss. For example, you will see a single shot after the 30 dB has the longer long-tailed postcursors and the bigger first precursors than the one after the 20 dB. Also, you will see the main cursors of the single shot after the 30 dB has a lower pulse amplitude than the single shot after the 20 dB loss. In addition to the loss, what else channel behavior would you care about? Think about the impedance image for 5 seconds. Right. Second, the single shot shows the fundamental representation of a channel reflection behavior. If there's any impedance mismatch causing the discontinuity in the channel interface, you might see the reflection behavior from the eye diagram in a low loss. But do you see the reflection image from a high loss and high reflective eye diagram? Of course not. Then you should know how the single shot would help you easily visualize if the channel has a serious discontinuity. Besides the insertion loss and the return loss of the channel behaviors, what else you might want to know? Great. Third, the single shot shows the fundamental representation of channel latency behavior. Definitely, you cannot see the latency behavior of the channel from the eye diagram because the time domain information has been hidden without showing the causality. But someone may ask if the latency is important. Good question and correct. For the high-speed SerDes, the channel such as PCB baud traces, backplanes, or cable are very short, and the delay should be in the range of a few nanoseconds. So, most of the time our applications we don't care about the channel latency too much. Then, what should we mention here? And use the single shot to check the latency? Bingo! Sanity check of the model validation. You should know if the S parameter you simulated was reasonable. For example, you might need to simulate your channel model in your ISI or SI test bench. For some reason, the channel model was not created properly, and it was a non-causal system. If the single shot caught the modeling error or mistake earlier, you should not waste your time debugging your ISI or SI simulation issue. Instead, you will go back to the channel model debug efficiently after understanding the channel behaviors from the single shot. What else could you learn from it? Perfect. Fourth, signal and system. Only the channel does not mean anything. But again, the eye diagram cannot easily show the relationship between the high-speed signal and the high-loss channel. Instead, the single shot can show how the different path width and transition time were impacted by the 30 dB loss channel. For example, you can see a sharper transition time over a wider path width of a single shot may have a higher pulse amplitude at the main cursor than the slower transition time over a narrower pulse width. On the other hand, a sharper transition time over a narrow pulse width might have a bigger sensitivity from the channel's discontinuity. Those observations from both the signal and system will help you easily understand how to recover the signal after the channel from distortion or bit errors. After understanding the relationship between signals and channels, we can even implement an efficient channel validation tool. What's that? Think about the image of 1 million bits for 5 seconds. Bingo! To extrapolate the peak-to-peak RJ for bit array down to 1e-12 precisely, a corresponding measurement from the transitions of about 1 million bits is a must. Even though extending the tails down to 1e-12 is an extrapolation of at least 6 orders of magnitude, the estimation of sending 1 million bits is still impossible to do in a reasonable simulation time. Therefore, what should we do to speed up the simulation time of the 1 million bits? Think about the convolution image from your signal processing 101 class for 5 seconds. Great. The output signal of any digital transmission can be modeled as the convolution of the input data sequence with the channel's single shot response, which directly shows you how each bit of data will be shaped and spread across time. This single shot response convolution over a series of bit streams in a super precision capture or verify the following behavior, including ISI, equalization, DJ, and RJ over multiple bits periods. Then the Holding evaluation over budget can be verified for a very low bit array target. Here are the summarized images showing you why you need a single shot response or single shot for inter-symbol interference ISI analysis. Again, a single shot is a handy tool for analyzing ISI compared to the eye diagram because it shows exactly how a channel affects a single bit of data and how much that bit spread into adjacent timestamps. Instead, the eye diagram will cross at 20 dB or 30 dB and cannot provide much difference or insights into ISI. But understanding this ISI spread and discontinued reflection, engineers can design the link budget to improve the SI. In addition, a single shot shows how the channel has impacted the signal's path width and transition time in higher data rates and greater channel loss. So, designers know the design trade-offs. Again, single-shot analysis is crucial for link SI analysis as it provides insights into signal behaviors, including the ISI and reflection effects, informs system design and aids in performance optimization. Finally, the single-shot response along with the convolution of a big string can speed up a channel or link simulation of a series up to 1 million bits for precise low bit array evaluation. This channel simulation tool is key to maintaining the integrity of high-speed data communications. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.